Hi everyone, welcome back. In this lecture I'd like to talk about vector projections or projections of vectors. So here's the setup. We're going to draw a picture here. Let's suppose we have one vector, let's call this one u, and another vector, let's call this one v, and I'm going to draw v as kind of horizontal. And the arrangement of these vectors doesn't have to be exactly like this, but I like it this way for the sake of drawing the picture now. And here's the deal. What we want to try to do now today in this lecture is try to imagine that we could stand, let's say that we were standing directly above, this is us, directly above this vector and shining a light. Okay, so we're shining a light, and the light then casts a shadow. And the shadow of this, I'm going to draw this like a green, it goes straight down. Let's suppose that that's perfectly perpendicular. All right, and so the shadow on the ground from this shining light would look like this, right? This would be the shadow. So we're going to call this shadow, we're going to think of this as a vector and call this P. This vector P is called the projection of u onto V, the vector projection of u onto V. All right, so P here is called the projection. I'm going to write it in two ways, and the second way is much better. This is the way that we should always write it. So it's the projection onto V of u, the projection of v of u onto v, and like I said, we read this as the projection of u onto v. So our goal in this lecture is going to be to derive a formula that we can use to compute this vector p. So let's think this out a little bit. We have a couple of things going on here. First of all, the vector p is in the same direction as the vector v. So just by looking at the picture and thinking about the geometry here, the vector p has to be some scaling factor, I'll call it alpha, times the unit vector in the direction of the vector v. So to get the unit vector in the direction of v, we know how to do this, right? You take the vector v and divide it by its own length. And as I do this, I remember that I forgot to say something important that I also forgot in the last video a couple minutes ago here, but it's very important that v is not the zero vector here. V has to be a non-zero vector. And of course, for this picture to work out, we also want u to not be the zero vector. U can be the zero vector later once we have a formula, but for the sake of this derivation, we want the u to not be the zero vector. All right, now that we've got this, we need to think about what alpha is. In the picture that I've drawn here, this is our like motivational picture, alpha is just going to be the length of the vector p. All right, so alpha is equal to the length of this vector p that we're trying to find, the projection. We're going to call it the projection later, but just for the sake of this computation, I'm calling it p. But there's one issue here, and that is that it's possible that our vector p could point in the other direction. So I'll draw a scenario where that might happen. If our vector u is over here and our vector v is this way, then actually when we shine our light, we would have to extend this vector v this way, and the vector p would actually be pointing in the opposite direction. So the alpha would then be negative, right? The alpha would not be just the length, it would be negative. So I'm going to just say it's plus or minus p, and actually we'll see that in the computation, it's going to take care of this for us, okay? But for the sake of this argument, let's say that alpha is equal to, again, just by this picture, right? And then we can generalize, but by this picture, let's say that alpha is equal to the length of p. So this p hat is then going to be equal to the length of p hat times the vector, the unit, so this is a number, right? So it's a scaling factor, times the unit vector in the direction of v, which is v over length of v. We need to try to represent the length of p in terms of just u and v. All right, and so the way that we're going to do this is go back up to our picture and think about the fact that we have a right triangle here. We have the angle theta, and our shadow has made a perfect right triangle, and that was one of our assumptions, right? Our projection is, it forms a perfect right triangle. It's directly below the vector u. From here, we can now just use trigonometry, right? Because the cosine of this angle is the adjacent side length divided by the hypotenuse length, right? So just by using trigonometry here, the cosine of theta must be the length of p divided by the length of u. All right, so I'm going to scroll down and then we'll work with this, but here we go. So we know just by what we just wrote down, right? The length of P must be equal to, the length of P divided by the length of U, must be equal to the cosine of theta. And I left some room here because I'm going to do a couple of things. First of all, I'm going to take this U and put it onto the other side, right? So we assumed the U, that our vector was not the zero vector, right? And so I'll put the vector U here. And then at this point, I don't really need fraction symbol, so I'll get rid of that. All right, and then the next thing I'm going to do is the following. Again, neither of our vectors is the zero vector, right? So at this point, v is not 0. So what we can do is multiply by the length of v divided by itself, right? Length of v over the length of v. That's just 1. So we haven't changed this at all. And so at this point, we see, hopefully you recognize this from the last lecture video, hopefully we see that this term right here is just the dot product, right? This is the dot product of u with v. This is our alternate formula, our geometric formula for the dot product. And so what we've learned here then is that this length of p in the picture that I drew is equal to the length of u times, well, I just wrote that, right? So it's equal to the dot product of u with v. That's what we worked out here, right? So u dotted with v divided by the length of v. And now we remember that the dot product can absolutely be negative, right? The dot product is negative when theta is between pi over 2 and pi. So in this case, when our vectors form an angle that's larger than pi over 2, then the dot product will take care of our plus or minus issue that we had right here. So this is actually, after all the work, we used the triangle that we had to derive this, but this is actually our alpha that we were in search of in the first place, right? And so what we've done then is derived a formula for that projection vector P. So P is the projection onto V of U, and it's given by this formula alpha, which is u dot v over length of v, times the unit vector in that direction of v, right? So times v over length of v. All right, so this is called the vector projection of u onto v. So it's vector projection. I'll just leave it like that. And it's denoted by proj sub v of u. Okay, so the subscript is the vector that's being projected onto, and the argument here that's on the same line as proj, like this is kind of below a little bit, right? It's a subscript, and this one is the vector that's being projected. When you compare over here on the right hand side, you see a u, and then all the other variables are v's, right? Keep in mind this is a number, and this is a vector. So we get a vector in the same direction as v. All right, I like this version because it also gives us something called the scalar projection, or the component projection, and that is actually exactly alpha. It's the reason we had alpha before, right? This turns out to be the scalar projection because this is a number. And remember, numbers are called scalars in vector speak, right? But it's also the component. It's like a component. So it's called comp. This is a notation that we use. Comp sub v of u. And again, it's exactly this scaling factor. It could be negative, right? Exactly the scaling factor. So this is u dot v over length of v. And so then we see the relationship between the vector projection and the scalar projection. So this is the scalar projection of u onto v. All right, we're going to do one more thing here. We are going to, well, two more things, I guess. We are going to write down a formula for a different formula for this projection, because we can take advantage of the fact that this is a product of lengths down here. So our projection, this is an alternate formula. Our projection onto v of u is equal to u dot v over, you can multiply these together. This becomes length of v quantity squared times v, right? So that's exactly the same formula. It's just combined. And so now this right here is a number. It's a scaling factor. And this is the direction vector, but it's not a unit vector anymore, right? But the reason that this might be better is because when you look at this bottom term, the length of v squared we know is just v dotted with itself, right? So another form of the formula for the projection vector is that it's u dotted with v divided by v dotted with v all times v. And now again, you see 1u, v, 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 all kinds of v's, right? So the vector that you're projecting onto does almost all of the work at this point. All right, the vector u plays a role, obviously, and it's related, the role that it plays is related to its length, of course, and the angle. So, yeah, which are the two parts of it, right? The direction and the magnitude. So obviously it plays a role. All right, back up to the picture one more time. I'm going to keep this lecture kind of theoretical, where we just derive these formulas, and then we'll do examples in the last lecture video. But there's another vector here. This vector right here, this vector is now a vector which, if you go over in the projection of u onto v, this proj, and then this one goes straight up, right? And so this one's called the orthogonal projection, or orth of v, u onto v again, but it's not really onto anymore because it forms a perfect perpendicular complement in some sense to this projection vector p. And if we look at this, let's see, where does this come from, right? Well, it's connecting tip to tip of these two vectors, right? And it's exactly then u minus the projection vector p. Okay, so I'm going to scroll down and write this formula, but you can see exactly how this is going to work. And you might have to work this out in the future. So orth, by the way, one of the reasons we care about orth and proj at the same time is that proj and orth now obey kind of like the right-hand rule, right? They're perpendicular to each other. Proj is in the direction of v, so if v is important to us, then p will have the same direction as v. For those of you who want to become engineers, you can think of frames, moving frames for either mechanical devices or traveling particles, airplanes, stuff like that, right? So p is in the direction of your v vector, might be a velocity or something, and then this orth is then, and it's, you know, it's related to u, so you have some other information, some other vector u, think of it maybe a force or something, and then p is the projection of that force onto your direction of your velocity, and then the orth is going to be perpendicular to that, right? So orth sub v of u is just going to be u minus proj, and I'll write out the formula, but we know exactly what it is here, right? And so this is u minus, and we just write this formula here, u dot v over v dotted with v times v. All right, so that's the orthogonal component, the orthogonal projection.